August 17, 1943. Patricia Lake, Alberta, Canada. Lieutenant Commander James Fraser's boots crunched through fresh snow as he approached the most unusual structure he'd ever seen floating on these remote waters. The massive rectangular hull, 60 feet long, 30 feet wide, 20 feet deep, sat impossibly low in the mountain lake, its surface glistening with a strange, fibrous texture that looked nothing like ordinary ice. Fraser knelt at the waterline, running his gloved hand across the hull. It was cold, certainly, but something about the material felt wrong, too solid, too dense. He pulled off his glove and pressed his bare palm against it. The surface was rough, almost woody, embedded with fibers that gave it an organic quality. This cannot be standard ice. No naval architect would build a vessel from material this unusual unless... He stood and walked the length of the prototype, noting the complex system of pipes running through its interior. A refrigeration plant powerful enough to keep 1,000 tons of material frozen even as the August sun beat down. The hull showed no signs of melting, no pooling water, no structural weakness. Fraser examined the areas where .303 rifle rounds had been fired into the material during tests. The bullets had barely penetrated 6 inches. On standard ice, they would have shattered through completely. This was not ice. This was something else entirely. The implications were staggering. If this material performed as specified, it would revolutionize naval warfare. A vessel built from this substance would be impervious to torpedoes, resistant to bombs, and practically unsinkable. The British Admiralty's most audacious proposal, an aircraft carrier built from frozen water, might actually be possible. But Patricia Lake was remote, hidden in the Canadian Rockies, far from prying eyes. This prototype existed under absolute secrecy, codenamed Project Habakkuk, known to fewer than 200 people worldwide. Fraser knew why. If the Germans discovered what the Allies were attempting, they would either copy the design or dedicate everything to preventing its completion. Because floating in this mountain lake was proof of concept for the most ambitious naval construction project ever conceived. A 2,000-foot-long, 2.2-million-ton aircraft carrier built from a revolutionary composite material called Pykrete. A vessel so massive it would dwarf any battleship ever built. An unsinkable island that could close the mid-Atlantic gap and turn the tide of the Battle of the Atlantic. The prototype before Fraser represented 18 months of theoretical work, engineering breakthroughs, and increasingly desperate strategic calculations. It was the physical manifestation of Winston Churchill's belief that conventional thinking could not win this war. And it all began with one eccentric inventor's impossible idea. The journey to this frozen prototype in the Canadian wilderness had begun 2 years earlier, in the autumn of 1941, when the Battle of the Atlantic reached its most desperate phase. U-boats operated with near impunity in the mid-Atlantic Gap, a vast expanse of ocean beyond the range of land-based Allied aircraft. From this sanctuary, wolf packs intercepted convoy routes, sinking merchant vessels faster than Allied shipyards could replace them. In November 1941 alone, U-boats sank 62 Allied ships totaling 276,795 tons. December brought 55 ships and 229,949 tons lost. By February 1942, losses exceeded 400,000 tons in a single month. Britain's survival depended on the Atlantic lifeline. The island imported 70% of its food and virtually all petroleum. At current loss rates, the Admiralty calculated Britain would be starved into submission by mid-1943. Traditional solutions, building more escort destroyers, deploying more long-range patrol aircraft, could not close the gap quickly enough. The fundamental problem was geometric. The mid-Atlantic gap covered approximately 600 miles of ocean, too far for aircraft operating from Britain, Iceland, Greenland, or Newfoundland to patrol effectively. What the Allies desperately needed was an unsinkable aircraft platform that could be stationed in the middle of the Atlantic, providing air cover over the gap. But aircraft carriers were precious resources, expensive to build, vulnerable to U-boat attack, and required in every theater of war. The Royal Navy possessed only 6 fleet carriers in early 1942, and losing even one to a torpedo would be catastrophic. Into this strategic quandary stepped Geoffrey Pyke, one of the most eccentric and brilliant minds Britain possessed. Educated at Cambridge, Pyke had worked as a journalist, inventor, and advisor to Combined Operations Headquarters under Lord Mountbatten. His mind operated in unconventional channels, proposing solutions others dismissed as impossible. In early 1942, Pyke focused his considerable intellect on the aircraft carrier problem. His initial proposal was characteristically bold: capture icebergs, flatten their tops, and use them as floating landing strips. Icebergs were already unsinkable, immune to torpedoes, and freely available in the North Atlantic. The concept had merit, but significant problems emerged immediately. Natural icebergs were unstable, prone to rolling, and melted too quickly when towed to lower latitudes. They could not be shaped or modified easily, and they offered no protection for aircraft, crew, or supplies. Pyke needed something better than natural ice. He needed a material that combined ice's abundance with the structural properties of steel. In collaboration with Dr. Max Perutz, a crystallographer working at the Cavendish Laboratory, Pyke experimented with ice composites. They discovered that mixing approximately 14% wood pulp with 86% water before freezing created a material with extraordinary properties. This composite, which Perutz dubbed Pykrete in honor of its inventor, possessed compressive strength approaching that of concrete. Tests demonstrated that Pykrete was slower to melt than pure ice, absorbed bullet impacts without shattering, and could be sawed, shaped, and machined like timber. Most remarkably, torpedoes and bombs created only localized damage. Pykrete would not splinter catastrophically the way ice did. The material could be produced cheaply using seawater, wood pulp from Canadian forests, and refrigeration equipment. A vessel built from Pykrete would require no steel, a critical consideration given that Britain's steel production was entirely consumed by existing military demands. Pyke presented his concept to Lord Mountbatten in December 1942. Mountbatten, chief of Combined Operations and a man who appreciated audacious thinking, immediately recognized the potential. He commissioned detailed engineering studies and arranged for Pyke to present the proposal to Winston Churchill himself. Churchill's reaction to Project Habakkuk was characteristically bold. The Prime Minister, conducting business from his bath when Mountbatten first explained the concept, reportedly declared it wonderful and demanded immediate feasibility studies. The strategic logic was compelling. A Pykrete aircraft carrier stationed at 35 degrees west longitude would provide continuous air cover over the entire mid-Atlantic gap. Fighter aircraft launched from its decks could intercept Focke-Wulf Condor reconnaissance planes that spotted convoys for U-boat wolf packs. Torpedo bombers could attack U-boats detected on the surface. The vessel itself, immune to torpedo attack and resistant to bombing, would require minimal escort protection. By January 1943, engineering teams had developed preliminary specifications. HMS Habakkuk would be approximately 2,000 feet long and 300 feet wide, nearly 3 times the length of the largest contemporary battleship. The hull would be constructed from Pykrete blocks 40 feet thick, providing absolute protection against torpedoes, which typically detonated with insufficient force to penetrate more than 20 feet of the material. The flight deck would accommodate 150 twin-engine fighter bombers or 200 single-engine fighters. Below decks, the vessel would carry quarters for 3,600 crew members, workshops, ammunition magazines, and fuel storage for both aircraft and the refrigeration plant. Displacement was calculated at 2.2 million tons, more than 10 times that of the largest battleship ever built. The refrigeration system would be the vessel's circulatory system, pumping coolant through 2.5 million feet of piping to maintain the Pykrete hull at -16 degrees F even in temperate waters. Engineers calculated the refrigeration plant would require 1,880 tons of refrigeration equipment and consume 10,000 horsepower continuously, roughly equivalent to the power output of 4 destroyers. The vessel would be slow, maximum speed calculated at just 7 knots. But speed was unnecessary. HMS Habakkuk would be a mobile island, not a warship in the conventional sense. Once positioned in the mid-Atlantic, it would remain relatively stationary, requiring repositioning only as strategic conditions changed. Construction methodology was revolutionary. Rather than using traditional shipbuilding techniques, Habakkuk would be assembled like a massive ice cube. Work would begin in a northern lake or fjord during winter. Workers would construct the outer shell first, spraying Pykrete mixture onto a framework and allowing it to freeze. As construction progressed, refrigeration equipment would be installed within the growing hull, then powered up to maintain the structure once temperatures rose above freezing. Cost estimates varied, but planners calculated Habakkuk could be built for approximately £700,000, a fraction of the $2.5 million required for a conventional steel fleet carrier and requiring none of the precious steel needed elsewhere. Mountbatten became the project champion, presenting it to the combined chiefs of staff in Washington and to Churchill repeatedly throughout early 1943. The Prime Minister remained enthusiastic, seeing in Habakkuk the kind of asymmetric solution that Britain needed. Conventional approaches would not win the war. Bold innovation might. In May 1943, Churchill ordered construction of a full-scale prototype to prove the concept. The National Research Council of Canada was tasked with building the vessel in absolute secrecy. Patricia Lake in Alberta was selected for its remoteness, cold winter temperatures, and proximity to lumber resources. By June 1943, construction began. Canadian engineers and laborers worked through the summer, building the rectangular hull, installing refrigeration equipment, and conducting material tests. The prototype, 60 feet long, 30 feet wide, 20 feet deep, displacing approximately 1,000 tons, was functional by August 1943. It successfully maintained its frozen state even as summer temperatures exceeded 70 degrees Fahrenheit. Rifle fire and explosive tests demonstrated Pykrete's remarkable durability. The prototype, floating on Patricia Lake, represented proof that HMS Habakkuk could be built. The physics worked. The engineering was sound. All that remained was the political will to proceed. But by mid-1943, the strategic picture that had given birth to Project Habakkuk began to change in ways that undermined its fundamental rationale. The most significant shift came not from enemy action, but from Allied technological advancement. In April 1943, the United States Navy deployed its first VLR, Very Long-Range Patrol Aircraft, B-24 Liberators modified for maritime patrol with extended fuel capacity. These aircraft, operating from bases in Newfoundland, Iceland, and Northern Ireland, possessed sufficient range to patrol the mid-Atlantic gap, albeit with limited loiter time. By June 1943, VLR aircraft had closed the gap. U-boat sinkings increased dramatically as Allied patrol aircraft caught submarines on the surface during transit or recharging batteries. In May 1943, remembered as Black May by the Kriegsmarine, Allied forces sank 41 U-boats while losing just 34 merchant ships. The exchange rate had reversed catastrophically for Germany. Grand Admiral Karl Donitz temporarily withdrew U-boats from the North Atlantic entirely, marking the turning point of the Battle of the Atlantic. Simultaneously, Allied diplomatic efforts secured access to air bases in the Azores. Portugal, maintaining precarious neutrality, granted Britain use of bases on the islands in October 1943. Aircraft operating from the Azores could reach the heart of the mid-Atlantic gap with fuel to spare. The geographic problem that Habakkuk was designed to solve was being solved by conventional means. Commander Geoffrey Pyke, assigned to evaluate Habakkuk's continuing utility, drafted a classified assessment in September 1943 that laid bare the project's diminishing relevance. VLR aircraft provided more flexible coverage than a stationary platform. The Azores bases were already operational, and Habakkuk, even if construction began immediately, could not be completed before 1945 at the earliest. There were additional concerns that testing had revealed. While the Patricia Lake prototype proved Pykrete's durability, it also exposed engineering challenges that would scale exponentially with a full-sized vessel. The refrigeration plant consumed enormous power, requiring either a nuclear reactor, technology still years from practical application, or diesel engines that would themselves require substantial fuel supply. The slow construction time frame meant Habakkuk would be vulnerable during the months-long building period before its refrigeration system became operational. Naval architects also questioned the vessel's survivability in rough seas. The prototype on Patricia Lake performed well in calm water, but the North Atlantic generated waves exceeding 50 feet. A vessel with 40-foot freeboard and minimal propulsion might survive such conditions, but its operational effectiveness would be severely compromised. Aircraft could not land or take off in heavy seas, rendering the carrier useless precisely when convoy protection was most needed. Cost estimates, initially favorable, crept steadily upward as engineers refined their calculations. By late 1943, the estimated cost approached £2 million, nearly as expensive as a conventional carrier and requiring 2 years to construct versus 18 months for steel vessels. Most fundamentally, the strategic calculus had changed. In early 1942, Britain faced starvation and defeat. By late 1943, the Allies were winning the Battle of the Atlantic through a combination of improved convoy tactics, escort carriers, long-range aircraft, advanced radar, and breaking the German naval codes. Habakkuk's window of necessity had closed. The examination of the Patricia Lake prototype in August 1943 provided proof of concept, but it arrived too late to matter. The very success of interim solutions, escort carriers, VLR aircraft, new bases, had rendered the revolutionary solution unnecessary. In December 1943, the project was formally terminated. The combined chiefs of staff concluded that resources allocated to Habakkuk could be better employed elsewhere. The war still required innovation, but not this particular innovation. The prototype on Patricia Lake remained frozen through the winter of 1944, maintained by its refrigeration plant as a testament to what might have been. In spring 1944, with the project officially canceled, the refrigeration equipment was removed and repurposed. Slowly, across the following summer, the massive Pykrete hull melted, releasing its wooden pulp fibers into Patricia Lake. By autumn 1944, nothing remained on the surface to indicate that Britain's most... The requirements that shaped HMS Habakkuk emerged from a brutally simple strategic calculation confronting Britain in 1942. The Mid-Atlantic Gap represented approximately 600 miles of ocean beyond the effective range of land-based aircraft. Convoys crossing this zone required 7 to 8 days to transit, during which they were vulnerable to U-boat attack without air cover. German submarines sank an average of 96 merchant ships per month during the first half of 1942, a rate that would deplete Britain's merchant fleet within 2 years. The solution required an aircraft platform that could operate continuously in the central Atlantic, 1,000 miles from the nearest land. Conventional aircraft carriers met this requirement, but were vulnerable to torpedoes and expensive to build. Britain possessed only 6 fleet carriers in 1942, all desperately needed in the Mediterranean and Pacific theaters. Lord Mountbatten's staff established specifications in January 1943. The vessel must accommodate at least 100 aircraft. It must be functionally immune to torpedo attack. It must be buildable without consuming steel resources. It must cost significantly less than a conventional carrier. And it must be operational within 18 months. The mathematics were brutally simple. A conventional Essex-class fleet carrier displaced 27,100 tons, carried 90 aircraft, required 17,000 tons of steel, cost $78 million, and took 20 months to build. Even if Britain had the steel, which it did not, and the shipyard capacity, which it also did not, traditional carriers could not be produced quickly enough to close the Atlantic Gap before Britain starved. Pykrete offered an asymmetric solution. The material could be produced from abundant resources, seawater and wood pulp. It required no steel, no exotic alloys, no scarce metals. It could be manufactured on-site, eliminating transportation bottlenecks. And its ballistic properties, compressive strength of 3,000 psi, equivalent to concrete, made it superior to steel hulls in one critical respect: torpedo immunity. Engineers calculated that a 40-foot thick Pykrete hull would completely absorb a torpedo detonation. The explosion would create a crater perhaps 15 feet deep, but the surrounding material would remain intact. Unlike steel, which could be ruptured catastrophically by a single well-placed hit, Pykrete would suffer only localized damage. 1,000 torpedoes could hit Habakkuk without sinking it. But these advantages came with severe trade-offs. First, size. To achieve the required displacement and stability with a material as heavy as Pykrete, 57 pounds per cubic foot, compared to steel at 490 pounds per cubic foot, the vessel had to be enormous. The hull alone would contain approximately 1.7 million cubic feet of Pykrete, weighing 2 million tons. This was not a weakness. Sheer mass provided additional protection. But it meant construction would be unlike any shipbuilding project in history. Second, refrigeration. Pykrete melted at 32 degrees Fahrenheit, far too warm for Atlantic waters in summer. Maintaining the hull required continuous refrigeration, consuming 10,000 horsepower. The refrigeration plant itself weighed nearly 2,000 tons and required constant fuel supply. Engineers calculated Habakkuk would need 1,000 tons of diesel fuel per month just to power the cooling system, creating a logistics burden that partially offset its strategic advantages. Third, mobility. The enormous displacement and low power-to-weight ratio meant Habakkuk would be slow, 7 knots maximum. This was acceptable for a stationary platform, but it meant the vessel could not reposition quickly in response to changing tactical situations. Once committed to a location, Habakkuk would remain there for months. Fourth, construction time. Despite using abundant materials, building Habakkuk would take at least 18 months from project start to operational deployment. The vessel had to be constructed during winter months when ambient temperatures supported Pykrete formation, then maintained by refrigeration through subsequent summers. This timeline meant decisions made in 1943 would not yield results until 1945 at the earliest. The designers faced an impossible choice: accept these limitations or abandon the project entirely. Geoffrey Pyke and Lord Mountbatten believed the trade-offs were justified. A slow, enormous, fuel-hungry platform was still preferable to no platform at all. The strategic value of closing the mid-Atlantic gap outweighed the engineering compromises required to achieve it. The decision to proceed with the prototype reflected this logic. If Pykrete performed as predicted, if the refrigeration system worked, if the hull could be constructed efficiently, then Habakkuk's limitations would be acceptable costs for solving an otherwise insoluble problem. At the time, in early 1943, this reasoning seemed sound. Britain was losing the Battle of the Atlantic. Conventional solutions were not working. Revolutionary thinking was required, and Habakkuk represented the most revolutionary proposal yet advanced. The designers were not naive. They understood the vessel's limitations, but they also understood that wars are won by solving critical problems, even if the solutions are imperfect. Habakkuk would solve the mid-Atlantic gap problem. That alone justified its existence. What they could not foresee was that other solutions, less revolutionary but more rapidly deployable, would solve the problem first. The consequences of Habakkuk's cancellation were both immediate and lasting, though not in the form of battlefield casualties. Unlike weapons deployed and found wanting, Habakkuk never faced the test of combat. Its impact came through what did not happen: the resources not expended, the conventional solutions pursued instead, and the lessons learned about innovation during total war. When the project was terminated in December 1943, the immediate beneficiaries were Allied resources redirected to proven technologies. The $2 million that would have funded Habakkuk's initial construction instead supported production of 12 additional escort carriers, small, mass-produced vessels that proved devastatingly effective at U-boat suppression. Each escort carrier cost approximately $166,000, carried 24 aircraft, and could be built in 6 months using existing shipyard techniques. By March 1944, 50 escort carriers operated in the Atlantic, providing air cover that rendered U-boats nearly impotent. These vessels, built from the same steel and resources that Habakkuk would have required, achieved Habakkuk's strategic objective through proven means. The calculus was stark: one theoretical superweapon or a dozen working platforms. The Allies chose quantity and availability over revolutionary innovation. The redirection of research talent yielded similar benefits. Engineers and scientists assigned to Project Habakkuk returned to conventional programs. Max Perutz, the crystallographer who developed Pykrete, redirected his expertise to studying ice formation on aircraft, research that improved cold weather operations for Allied bombers over Germany. Geoffrey Pyke moved to other unconventional projects, though none achieved the prominence of Habakkuk. The refrigeration experts who designed Habakkuk's cooling system applied their knowledge to cold storage facilities for Pacific operations, where tropical heat spoiled food supplies. The expertise developed for an ice ship found practical application in logistics infrastructure. Yet Habakkuk's cancellation also represented a broader shift in Allied strategy. Early in the war, Britain faced existential threats that demanded desperate measures. Habakkuk embodied that desperation, the willingness to attempt anything, however audacious, to avoid defeat. By late 1943, the strategic situation had stabilized. The Allies were winning, slowly but inexorably. Desperation gave way to systematic application of industrial and technological superiority. This shift had costs. The innovation that produced Habakkuk, the Mulberry Harbors, the bouncing bomb, and dozens of other eccentric solutions came from a culture that rewarded unconventional thinking. As the war entered its final phase, military procurement became more conservative, focusing on incremental improvements to proven designs rather than revolutionary leaps. Some historians argue Habakkuk's cancellation was inevitable and correct. The project consumed resources during feasibility studies that could have been applied elsewhere. The prototype, while successfully demonstrating Pykrete's properties, also revealed practical limitations that would have multiplied with scale. A full-sized Habakkuk might have worked, but it would have been expensive, slow to build, and potentially obsolete before completion. Others suggest Habakkuk represented the kind of asymmetric thinking that might have shortened the war. Had the project been approved in 1941 instead of 1942, had construction begun before VLR aircraft and Azores bases solved the mid-Atlantic gap, Habakkuk might have saved thousands of merchant seamen's lives by closing the gap a year earlier. The prototype on Patricia Lake melted into history, but the concept lived on in Cold War planning. In the 1950s, both American and Soviet military planners revisited ice platforms for Arctic operations. The U.S. Air Force operated research stations on ice islands in the Arctic Ocean, validating Pyke's core insight that frozen platforms could serve military purposes. None matched Habakkuk's ambition, but the principle, using ice as engineering, proved sound. The most significant consequence was doctrinal. Habakkuk demonstrated that revolutionary thinking could progress from concept to prototype in 18 months during wartime. This lesson influenced Cold War military development, where programs like stealth aircraft, nuclear submarines, and intercontinental ballistic missiles went from theoretical concept to operational deployment in compressed timeframes. The project also highlighted the danger of solving yesterday's problem. Habakkuk was designed for the strategic situation of early 1942. By the time engineering validated the concept in mid-1943, the situation had evolved. Military innovation requires not just technical success, but strategic relevance. Habakkuk achieved the former, but lost the latter. For the men who worked on the project, Canadian laborers building the prototype in Alberta, British engineers calculating specifications in London, American advisors evaluating feasibility in Washington, the cancellation was anticlimactic. They had believed they were building something revolutionary. Instead, they watched their work melt away. The final accounting of Project Habakkuk exists not in production statistics or loss rates, but in resources expended, knowledge gained, and lessons learned from an ambitious failure. Total expenditure on the project, from initial feasibility studies in late 1942 through cancellation in December 1943, totaled approximately £250,000. This included theoretical engineering work by Combined Operations Headquarters, material testing by Max Perutz and his team, construction of the Patricia Lake prototype, and administrative costs for managing a classified program across 3 nations. For comparison, a single fleet carrier cost £2.5 million to build. Habakkuk's research and development phase consumed 1/10 the cost of a conventional carrier while validating a revolutionary concept and providing knowledge that applied to other programs. The Patricia Lake prototype represented the largest single expenditure, approximately £100,000 for construction, refrigeration equipment, labor, and testing over 6 months. The vessel successfully maintained structural integrity from August 1943 through April 1944, when its refrigeration system was deactivated. It melted completely by September 1944, leaving no physical trace except refrigeration piping that sank to the lake bottom, where it remains today. Production of Pykrete for testing purposes totaled approximately 100 tons across various laboratories. Engineers determined the optimal mixture was 14% wood pulp by weight, 86% water. Compressive strength averaged 3,000 psi, sufficient to support the weight of a multi-deck superstructure and aircraft operations. Tensile strength proved lower but adequate given the hull's massive cross-section. Material testing revealed Pykrete's properties in detail. At -16 degrees F, the material exhibited minimal creep under sustained load. Thermal conductivity was 1.3 BTU per hour per square foot per degree Fahrenheit, slow enough that a 40-foot thick hull would require refrigeration only at the surface layers once initial freezing was complete. Ballistic testing demonstrated that .303 rifle rounds penetrated only 4 to 6 inches, while .50 caliber rounds reached 12 inches. Neither caused structural cracking beyond the immediate impact zone. No combat trials occurred, obviously, but engineers calculated theoretical survivability against standard German torpedoes. A G-7A torpedo carried a 280-kilogram warhead that detonated with approximately 500,000 joules of energy. Such an explosion would crater Pykrete to a depth of approximately 15 feet, well short of penetrating a 40-foot hull. Even a near-simultaneous double hit, unlikely given U-boat tactics, would not breach the hull. The comparative analysis with conventional carriers highlighted Habakkuk's theoretical advantages and practical limitations. HMS Illustrious, contemporary British fleet carrier. Displacement, 23,000 tons. Length, 743 feet. Aircraft capacity, 36. Hull armor, 4.5-inch steel belt. Construction time, 30 months. Cost, £2.5 million. Torpedoes required to sink, 2 to 3. HMS Habakkuk, proposed Pykrete carrier. Displacement, 2,200,000 tons. Length, 2,000 feet. Aircraft capacity, 150. Hull armor, 40 feet Pykrete. Construction time, 18 to 24 months. Cost, £2 million, estimated. Torpedoes required to sink, functionally impossible. The comparison revealed the fundamental trade-off. Habakkuk offered superior protection and aircraft capacity at the cost of mobility, 7 knots versus 30 knots, and operational flexibility. Personnel assigned to the project at various points totaled approximately 300 individuals. 150 Canadian laborers and supervisors at Patricia Lake, 50 British engineers and scientists conducting theoretical work, 50 American advisors and observers, and 50 additional support staff across logistics, security, and administration. No casualties resulted from the project. The most serious incident occurred during ballistic testing at Patricia Lake when a ricochet injured a technician's hand, requiring medical attention but not hospitalization. This safety record contrasted sharply with conventional shipbuilding, where industrial accidents killed approximately 15 workers per major vessel constructed during the war. The philosophical difference between Habakkuk and conventional solutions reflected broader patterns in Allied versus Axis approaches to military innovation. Britain, facing resource constraints and existential threats, sought asymmetric solutions that leveraged unconventional materials and radical designs. The United States, blessed with industrial capacity, preferred incremental improvements to proven concepts, producing vast quantities of good-enough equipment. Habakkuk represented the British approach at its most extreme. Solve an impossible problem by rejecting conventional assumptions. The project's cancellation marked a transition toward the American approach: solve problems through industrial scale rather than revolutionary innovation. In the final analysis, Project Habakkuk consumed resources equivalent to 1/10 of a fleet carrier's cost, while advancing engineering knowledge and demonstrating that frozen composite materials could serve structural purposes. The project failed not because the engineering was faulty, but because the strategic problem it addressed was solved by other means before the solution was needed. August 17, 1943, Patricia Lake, Alberta, Canada. Lieutenant Commander James Fraser stood at the waterline, examining humanity's most ambitious attempt to weaponize frozen water. The prototype before him represented 18 months of desperate innovation, eccentric genius meeting strategic necessity in the cold waters of a Canadian mountain lake. By the time of Japan's surrender on September 2, 1945, the Battle of the Atlantic had been won for 2 years. Allied merchant vessels crossed the ocean with impunity, their cargoes arriving intact, their crews surviving to make return voyages. The Mid-Atlantic Gap, the strategic void that gave birth to Project Habakkuk, had been closed not by a revolutionary ice fortress, but by a combination of conventional solutions: escort carriers, long-range patrol aircraft, advanced radar, and broken German codes. The final irony of Habakkuk was timing. Conceived as an emergency response to imminent defeat, the project matured into viability precisely as emergency measures became unnecessary. The prototype proved the concept in August 1943. By December 1943, the concept no longer mattered. The weapon that would have solved the crisis of 1942 arrived 2 years late to a battle already won. What Project Habakkuk revealed about military innovation remains relevant beyond its specific circumstances. It demonstrated that revolutionary solutions require not just technical feasibility, but strategic relevance maintained across the development timeline. Wars evolve faster than complex programs can develop. By the time audacious concepts become proven technologies, the problems they address may have been solved by conventional means, shifted to different theaters, or disappeared entirely through enemy defeat. Habakkuk also illustrated the value and limits of unconventional thinking. Geoffrey Pyke's insight that frozen composite materials could serve as naval construction material was brilliant and valid. The engineering worked. The prototype succeeded. But brilliance alone does not guarantee relevance. The best solution to yesterday's problem may be irrelevant to today's reality. The broader lesson concerns how nations innovate under existential pressure. Britain in 1942 faced starvation and invasion. That desperation produced Habakkuk, Mulberry Harbors, bouncing bombs, and dozens of other eccentric solutions. As the threat receded, innovation became conservative. The audacity that characterized Britain's darkest hour faded as victory became probable rather than impossible. Today, the prototype's refrigeration pipes rest on the bottom of Patricia Lake, artifacts of ambition too bold for its moment. The Pykrete that comprised the hull melted into water and wood pulp, its molecular bonds dissolved as surely as the strategic necessity that called it into existence. HMS Habakkuk was not poorly designed. It was brilliantly designed to solve a critical problem using unconventional materials and radical thinking. The design simply didn't include the one element that mattered most: arriving in time to matter. And in that single fact lies the entire story of how Project Habakkuk became history. A weapon that worked perfectly, except for being unnecessary. The examination of the Patricia Lake prototype in August 1943 provided final proof that humanity could weaponize frozen water, build unsinkable fortresses from wood pulp and ice, and station floating islands in the middle of the Atlantic Ocean. But it also proved that wars are won not by the most revolutionary weapons, but by the weapons that arrive when needed, work reliably when deployed, and solve problems that still exist when they become operational. Project Habakkuk solved a problem that vanished before the solution materialized. That may be the most successful kind of failure, a weapon so unnecessary that its absence changed nothing, saved nothing, and killed no one.